Welcome back. So far, we explored the foundations of inheritance, how base classes and derived classes relate, how we structure hierarchies, and how we represent them using UML diagrams. In this next part, we'll get more advanced. We'll compare composition versus inheritance, explore polymorphism, one of the pillars of OOP, and dive into the details of method overriding and access control. These are essential tools not just for reusing code, but for building flexible, adaptable, and safe software systems. Let's get into it. Let's clarify a common confusion: composition versus inheritance. Inheritance models an is-a relationship. A car is a vehicle. A rectangle is a shape. It means the derived class shares the identity of the base class. Composition models a has-a relationship. A car has an engine. An employee has a birth date. The logic: use inheritance when one class is a specialized version of another. Use composition when one class uses another as a part of its internal structure. This decision is central to good software design. Misusing inheritance where composition fits better leads to fragile, hard-to-maintain code. Now we explore a key OOP concept: polymorphism. The word means many forms. In programming, it means you can treat objects of different types through the same interface. Example: shape has a method draw. Both circle and square override draw. You can loop through a list of shapes and call draw, and the correct version will be called for each shape automatically. This is runtime polymorphism, and it's what makes object-oriented systems truly scalable and flexible. Overriding is how derived classes change or extend the behavior of base classes. Here's how it works. The method in the base class must be marked virtual. The method in the derived class must use override. Example: public virtual void honk is overrided in car class. Logic: the method name stays the same. The implementation changes, allowing customized behavior while still treating the object as its base type. This enables polymorphism. Objects behave correctly even when accessed through a base reference. Let's break down access levels. Public: accessible from anywhere. Private: accessible only inside the class. Protected: accessible in the class and its derived classes. Why protected matters: it allows child classes to interact with inherited fields or methods that are hidden from outside users. But use it wisely. Overusing protected exposes internals that may lead to tight coupling. Think of it as a controlled leak, just enough access for child classes to function without breaking encapsulation completely. Here's what we've covered so far in this section. Inheritance allows class reuse and hierarchy creation. Derived classes inherit methods and data, but access depends on modifiers. Use protected to let children access necessary internals. Overriding allows a derived class to redefine behavior cleanly. These concepts come together to support clean architecture and predictable class behavior. Now we see a base class in action: vehicle. Fields are private, not directly accessible. Properties give safe, controlled access. GetInfo is marked virtual, ready for overriding. This example reflects good design. Keep data hidden. Expose only what's needed. Prepare for specialization without guessing how it will be used. Here's how you represent the vehicle class in a UML diagram. Class name at the top: vehicle. Private fields listed with minus sign. Minus manufacturer, minus year. Public properties: methods with plus sign, plus manufacturer, plus year, plus GetInfo. This notation helps you and others visualize your class design and its relationships at a glance. UML diagrams are tools to plan, document, and communicate system structure before coding. Now we look at another base class: employee. Salary is private and accessed through a property. The setter applies a rule: salary cannot go below a threshold. The method getGreeting is simple, but can be overridden in child classes. This shows encapsulation in action. Internal logic is protected, while public methods offer a clean interface to the outside. Here's how we extend employee. Class commission, employee column, employee. The child class automatically gets all public protected members from employee and adds its own field, commission rate. Inheritance here saves you from rewriting fields like idnum and salary. It's a perfect example of specializing a general class. Let's see objects in action. In main, we create employees and commission employees. We initialize their inherited properties and set the new one, commission rate. This shows two things. Inherited properties work just like native ones. You can mix general and specific types in the same program. This is real-world modeling using OOP. Now we display all that object data. We use getGreeting for all, same method name. We display different values, salary, commission, etc. This is polymorphism in practice. You treat different types similarly, but each behaves according to its own logic and data. Clean, flexible, and scalable. We revisit protected. Remember, private equal no one sees it but the class. Protected equal children can access it. It's a design choice. You want to share control with subclasses, but still hide it from the outside world. But overusing protected can lock you into fragile designs. Think twice before exposing too much internal logic to children. In this example, salary is marked protected in employee. Commission employee can access it directly and reset it to 0. Had we kept it private, this direct assignment would fail. Again, protected equal inheritance level access, not public access. Use it when a child truly needs control, but design with discipline. Polymorphism means we can use one method name and let each object decide how it behaves. Examples: play, guitar strums, drum beats, operate, bicycle pedals, truck drives, satisfy graduation requirements, preschool checks attendance, college checks credits. This is the beauty of OOP thinking. Code doesn't need to care how an object behaves, just what method to call. Method. Overriding lets us customize inherited behavior. Base method must be marked virtual. Child method must use override. This signals clearly. This method may behave differently in derived classes. This gives us dynamic behavior. One interface, multiple results depending on the object. In the student class, the property credits is marked virtual. A derived class can override it to use different logic, say, calculate tuition differently. Overriding lets child classes redefine logic while still reusing structure from the parent. This is a core strength of inheritance, flexibility with consistency. Virtual methods unlock the full power of runtime polymorphism. A virtual method is like a placeholder. Each class down the hierarchy can provide its own version. Example: toString in every object in C#. Each class can override it to show a customized string. Again, don't confuse overriding with overloading. Overriding equals same name and signature, different classes. Overloading equals same class, different parameter list. Let's summarize the big ideas we've learned here. Inheritance gives structure and reuse. Composition is an alternative when you need HAZA relationships. Access modifiers, protected public-private control visibility, and influence class design. Polymorphism allows calling the same method on different types with different results. Virtual methods plus override unlock dynamic behavior at runtime. These tools make your classes not just correct, but powerful, modular, and future-proof. In the next section, we'll apply this by working with abstract classes and interfaces, tools that take polymorphism and design to an even higher level. Stay sharp. We're almost at the top of the OOP pyramid.